Proving an autonomous vehicle is statistically safer than a human driver requires billions of miles of road data. Accumulating that distance physically is constrained by time and capital, making it a difficult engineering target to reach through real-world driving alone. This graph plots driven distance against scenario coverage. The data follows a strict long-tail distribution. Everyday driving scenarios are covered on the left, but the fatal, complex edge cases live far down the right side of the tail, where the probability of them occurring naturally drops significantly. When we expand this gap, we see exactly what is missing: extreme precipitation levels, blinding solar angles, and erratic pedestrian trajectories. You cannot safely or reliably orchestrate these intersecting variables on a physical test track. This unclosed gap is known as validation debt. It represents an accumulation of unverified scenarios that remain embedded within the system's architecture as latent software defects. Relying on physical mileage accumulation does not inherently yield a safer system. The mathematics suggests that rare edge cases will likely remain unencountered before the vehicle is deployed. To address this mathematical reality, standard bodies like the SAE mandate a shift away from distance accumulation towards scenario-based testing, or SBT. This diagram outlines the three-tier architectural framework of scenario-based testing. It begins at the functional layer, which relies on high-level natural language descriptions of driving events, like a highway lane change in the rain. The logical tier defines the statistical distribution for that event. Environmental variables like vehicle speed and precipitation levels oscillate across a defined range of minimum and maximum bounds. Finally, at the concrete tier, those fluctuating variables lock into absolute mathematical values, creating a single, strictly defined, executable test case. Scenario-based testing provides a rigorous structural framework. Executing it, however, requires an engine capable of generating variations of those concrete parameters. High-performance virtual test platforms act as the digital twin execution engine for these concrete scenarios. Through procedural generation, the system can manipulate physical variables, recalculating road curvature or altering surface friction coefficients without the logistical setup time required in the physical world. Engineers can force the occurrence of highly specific optical edge cases. They can program exact solar glare angles or simulate the drop in illumination when a vehicle enters a tunnel. In physical testing, applying ground truth labels to the resulting data is a severe bottleneck. A human annotator requires hundreds of seconds to label a single frame of video, which limits the volume of data available for training. Virtual rendering engines bypass manual labeling by extracting internal data directly. Here, the raw frame splits into synchronized layers of semantic segmentation, 3D bounding boxes, and depth maps. Looking at the depth map, the engine maps exact pixel-by-pixel numerical distance metrics to every target object. Generating millions of consistently labeled frames reduces the risk of statistical coincidences caused by small physical sample sizes, aiding the AI model's ability to generalize to new environments. If a virtual environment relies purely on visual graphics, the AI model may learn features specific to the simulation that do not exist in reality, creating a performance gap when deployed on actual roads. To prevent this, the simulation must integrate physics-based solvers that compute exact optical, electromagnetic, and thermodynamic laws. This is the rendering equation, the mathematical foundation used to compute these environmental interactions. Within it is the bidirectional scattering distribution function, or BSDF. The BSDF variable dictates how a ray-traced LiDAR pulse scatters and reflects off a specific material texture, like wet asphalt. To measure the physical validity of the simulation, engineers use statistical metrics like the Pearson correlation coefficient and LiDAR hit ratios to compare virtual datasets against physical sensor data. When these correlation metrics are applied to physics-based outputs, virtual datasets have reached statistical similarities as high as 96% compared to raw sensor data, providing the needed evidence to use synthetic data for training. Validating the software is only the first phase. The physical hardware that will run the AI inside the vehicle must also be tested. Software-in-the-loop testing cannot account for the hardware's processing latency, communication bus noise, or real-time execution limits. This requires hardware-in-the-loop, or HIL testing, which integrates a physical electronic control unit directly into the virtual simulation's closed loop. The validated simulation environment is converted into an electrical bit stream and injected directly into the ECU's hardware. By bypassing the optical lens entirely, this direct data injection allows the processor to treat the signal exactly as if it came from a physical sensor. The physical hardware calculates its response, such as a braking command, and feeds that output immediately back into the simulator's vehicle dynamics model. Hardware in the loop verifies both the logical soundness of the AI algorithm and the real-time operational stability of the physical silicon under load. Executing this process requires moving massive amounts of synthetic data into the hardware without introducing artificial latency. Advanced driver assistance systems utilize high-speed SerDes communication interfaces, specifically protocols like GMSL2 and FPD-Link4. These specialized cables possess the bandwidth required to push uncompressed, high-frame-rate digital video directly to the ECU in real time. Inside a single cable, the architecture utilizes virtual channels. This allows up to 16 distinct data streams from surround view cameras and radar to travel in parallel to the centralized hub. Emulating these automotive serial protocols at the hardware level is the final technical step to achieving zero latency transfer between the virtual environment and the physical processor. We can apply this entire pipeline to a high-risk scenario, an automatic emergency braking system operating at night in heavy rain as a pedestrian in dark clothing steps into the roadway. Repeating this test on a physical track poses a threat to human stunt workers and relies on the difficult task of controlling precipitation and ambient light levels. Inside the simulator, engineers lock in the exact concrete parameters, setting the pedestrian's clothing reflectivity and establishing a precise occlusion percentage. The synthetic rendering of the storm is translated and injected via the GMSL2 protocol straight into the physical camera ECU of the vehicle. This table compares the physical baseline data against the injected virtual results. The ECU's time-to-collision braking response clocks in at 1.2 seconds for the physical test and 1.18 seconds for the virtual test. A 2TC variance under 2.3% indicates a high degree of deterministic similarity for this scenario. By aggregating results from thousands of such comparisons across different conditions, developers build the statistical evidence needed to validate the simulator's physical accuracy. This closed-loop testing methodology maps directly to the safety regulations governing the autonomous vehicle industry. Hardware in the loop fulfills ISO 26262 functional safety requirements by enabling systemic fault injection. Engineers can simulate severed communication cables or data bit errors to verify the system correctly defaults to a safe state. Additionally, it satisfies ISO 21448, known as SOTIF, by utilizing stochastic search across the virtual platform to isolate and mitigate the unknown unsafe scenarios classified as Area 3. Regulatory bodies are moving toward digital homologation. Instead of demonstrating millions of physical miles, vehicle licensing will increasingly require passing certified, standardized virtual scenario sets. Transitioning to a physics-based, HIL-integrated virtual testing pipeline is the core technical bridge to legally and safely deploying autonomous systems on public roads.